Welcome to our power quality improvement technique. We will discuss this PWM converter for the voltage source inverter, PWM technique for it. This is our second lectures on it. We were discussed the basics of this PWM technique at the third harmonic injections. Now we shall continue with the bipolar PWM. It is quite little primitive kind of thing, we generally do not use nowadays, we prefer the unipolar PWM, but anyway for sake of evaluation we shall study these methods also. Here we have seen that this is the switch and it is a 4 switch has been employed, and for this reason it is a full bridge configuration. In previous configuration, the previous class was the half bridge configuration. So, ultimately you know that if modulating wave is more than the triangle, then upper switch TA and the TV will be on, and otherwise the reverse TV and minus TA will be on. So, in this case the output waveform of leg A is generated by the comparison with the V control and the V try leg B with the leg B is negative of leg A. That means, if the pulses, if you give here whatever pulses, you will feed to a NOT gate and you give it here. That means, if this one is on and this one is off. So, same way whatever pulses you are giving here and you will put a NOT gate and give it here. So, leg B is the negative of the leg A. So, for this reason what happen, we will find that the different combinations of the switches, how it will work. So, there is a pair of the switch which may work is TA and minus TB. So, this is the path of power. So, for this reason and just reverse, that is minus TA and plus TB. So, you get the pulses and the output leg B is negative of leg A, that was the logic we have seen. So, output voltage will be VOB equal to minus of this logic, and thus it will be minus AO, and this output voltage will be 2 VA0T. This is a full bridge configuration, you will get a double the voltage because you are utilizing the full DC bus. So, peak of the fundamental will be MA into VD and its maximum value is limited to 1, and you know that for the square wave operation it is 4 Vm by 2 pi was for the half bridge and 4 Vm by pi will be for the 4 bridge. So, this is the your magnitude of the fundamental voltage you can expect. So, how does it work? So, this is the part of the 1 by f, that is the T, it may be 1 kilohertz, that is 1 millisecond, and you have a V control and the V try. You can see that this voltage positive as well as negative. So, for this reason we call this as bipolar PWM. So, voltage stress is quite high because it is switching in half cycle positive to negative, but difference of the voltage will come and that will be effectively a positive half of the sine wave. And here you can see that negative area is more and this will give you the negative part of the sine wave, but problem lies since it is switching over this point to this point. So, stress of this voltage is quite high, the device's rating required to be higher. So, let us come to the unipolar PWM. So, logic will be little different here, and we require to generate the sine or the modulating wave and negative of the modulating wave, not the NOT gate that which we have used in case of the bipolar PWM. The leg A and the leg B of the full bridge inverter are controlled separately. It is not that leg A is a function of leg B. What happened, leg A as a logic and you just complement the leg B and thus you get the voltage, and for this reason it is bipolar. And in this case what happened, there is a logic leg A V control is greater than V try for TA plus on and VAN equal to VD, and V control is less than V try on and that equal to minus Vn equal to 0. Similarly, you can have a 0 logic sometime, it is not that positive VDC or the negative VDC. So, you can boil down to the 0 voltage sometime. So, and it will cancel this 2 pole voltage, ultimately you are taking this voltage between these 2 points. So, this is the load to be connected in between. So, A and B you are interested to take the voltage. So, if there is the same voltage they will cancel. So, minus V control is greater than try, then TB will be on, and ultimately you will get the VBN equal to VD. Similarly, the V control is greater than V try, you will get minus TB on and that will be again this value will be equal to VBN equal to 0. So, thus you require 2 modulating waveform and 1 carrier waveform. You got this is a V control and this is minus V control. This is for leg A and this is for leg B. So, this will be the waveform pattern for leg A and this will be the waveform pattern for the leg B, and you sum it up, you get this voltage. You can see that there is no negative pulses in positive half cycle, and similarly reverse, there is no positive pulses in the negative part of the sine wave. The stress across the switch is going to be low, and also it shift the harmonic spectrum quite high. Another important issue we require to discuss, I know a student required to implement this active rectifier, power quality conditioners as a hardware and in master's level or the BTech level. So, we require to deal with the switches. Because of the finite turn on and a turn off time of the switches, you wait for the blanking time. So, you require to wait, because unless if you go back, since there is a diode and current you cannot give a flow. So, if this is the current it is flowing, then ultimately if you turn on this and you cannot instantaneously change the direction of the current, then first it will go off, diode will take up, then you can switch off the directions of, then you can change the direction of the current. So, you wait for that is called the blanking time TD after switching one switch off in a leg before the switching of the other switch of the same leg. The blanking time will increase or decrease the output slightly depending on the direction of the load. Sometime if it is upper diode is conducting, generally it is goes up in a positive half cycle, and if it is a same happens as reverse criteria happens if it is negative diode part of the switches has been conducting for the diode. So, it may add up the load current or the subtracted load current depending on the which devices is conducting. But for the worst case of design we will consider that we will add up the load current. Also, additional high frequency appear in the output voltage waveform, that is quite important phenomena. So, you will have a high frequency part, it is coming due to the diode. and that is uncontrolled because you are not controlling it. Unless the current directions will change till the current through the diode decays, then only, otherwise it will wait. So, that is called the blanking time. So, you have to wait for that time. This is some example of this dead time effect, and you have to give a little time for the legs, so that you cannot, so that short does not occurs. You have studied effect of the source inductance in basic power electronics, where you have essentially overlap angle between the two thyristors, that is called mu, and in between there is no power being transferred because of the shorting of this one leg of the thyristors. But what happened, since current was low, the shorting was not a problem, but here if the short occurs, then your high current will flow and DC bus will sink. So, that is a great challenge itself. So, for this reason we generally do not allow this current to we provide a dead time, so that no current flows, the legs is not been shorted, except one topology, or the topology derived on that directions, that is called jet source inverter. There we provide the shoot through by shorting the leg. So, this is the triangular wave and this is the modulating wave, and this is your ideal transition. Q1 was on and Q1 will go on conduction mode. So, this is the voltage across it. So, your voltage will drop to 0 ideally, and after that it is ideal transitions. It will take some time again to rebuild its voltage blocking capability, and this time is your TD. Similarly, let us assume that your lower device is named as Q4. So, it was conducting and it will get its forward blocking capability after the delay of the TD, and thus what happen, if you have the VAO and assuming that current is positive, it is in a positive cycles, if there is a lagging power factor, there is a challenge that will come little later. Voltage is positive, but since being a lagging power factor, current is still in negative half cycles. Assume that this is a case, so current is positive, then what happen, there is no problem here. So, ultimately since current was flowing through this and direction of the current was through this, so automatically when it is put off, this will be turned off. But if the directions, but once this lower devices comes into the pictures, then once it is regained, then there will be a challenge diode will come into the pictures, current D1 will current will flow through T1, and just reverse will happen if current is actually going out from this point, from the nodal point. So, it is minus A. So, you can see that if you turn it off this devices Q1, so initially it will not go through this path because it is sinking, ultimately current will try to flow through the diode first, thereafter it will go through the devices. And so, for this reason you will have a loss area will be this. So, depending on the lagging or leading power factor, so this is basically these devices, for these devices there will be a turn on loss if it is the lagging power factor. If it is a leading power factor, you will have a turn off loss. So, accordingly we require to design your dead time so that you can mitigate this loss. So, what happened actually? So, the current and the voltage feedback compensation we are talking about, we are not coming into the control system right now. Control system has to mitigate this problem now, and let us assume that voltage and current are being phase lag by phi. This is a voltage, and ultimately what happen if till this time when voltage is positive and current is negative, then once you turn off, you will get a little more voltage, and ultimately voltage will add up to the loss. Ultimately, please understand it that this part, it is regenerative part, voltage is positive, current is negative. So, thus what happen, it will continue till like that, and you also get a benefit from here, you will get a little higher voltage because of the regeneration, you have to feed it back. Basically, you are feeding back it here, and thus you will generate little more voltage, and after that it will be compensated. So, current and voltage feedback compensation generally used to minimize the waveform distortion. So, generally what happen, if voltage, most of the cases we have a inductive load and thus current is lagging. So, till the lagging portion you will get little more voltage, but fortunately the advantage is that it occurs at the very beginning of the zero crossing. So, stress across the machine is not high, and ultimately what happen if this comes due to this blanking, generally voltage will come down little bit, and that also good some way because stress across the switches get reduced. And here after the zero crossing again, since voltage become negative, current still positive, it will boost up the voltage again in regenerative region. Thereafter again it will be there. So, ultimately this extra energy has to be taken and compensated from this when there is a voltage and current are in a same wave cycle. So, now let us talk about very important aspect of this PWM technique, that is called the space vector modulation. This is quite important because most of the drives and as well as the D-STATCOM and your shunt active power filter all uses now space vector modulation because of the greater utilization of the DC bus voltage and more attuned to the SRF, because we have discussed already the SRF. So, SRF, that is the synchronous reference frame, it can directly fit to this SRF based grid connected inverter or converter as solar inverter or shunt active power filter or D-STATCOM or DVR. So, for this reason we require to discuss this space vector modulation technique in detail. So, the space vector modulation technique is an advance, of course, it is more computationally more complex and computationally intensive technique that offers, that is more important, why you will go for that performance, superior performance in variable speed drive as well as a shunt active power filter and DVR, UPQC both. This technique has the advantage of taking account of interaction among the phases when the load neutral is isolated from the central trap of the DC supply. So, generally this is the one aspect we require to understand very well. So, this technique has the advantage of taking account of the interactions among the phases, that is when load neutral is isolated, mostly it is a case we have studied, we have discussed just now, that is for the 3-way system, and if you have a third harmonic injection and you do not connect the star connected load midpoint to the midpoint of the capacitor, then it does not supply. Same way here, when the load neutral is isolated from the central of the DC supply, then there will be a balance of the voltages. Moreover, the space vector modulation technique can be used to minimize the harmonic, that is something we require to understand in detail, to minimize the content of the 3 phase isolated neutral loads, that is for the 3 phase 3 wire system. Generally, we have discussed for the grid connected inverter also a voltage source converter, that is we have a 3 phase representations, space vector representations of the 3 phase quantities, that is XA, XB, XC we have already discussed, with a space distortion of 120 degrees or the space distribution of the 120 degrees, pardon me, with X can be voltage, current or flux also in case of the machines, that is 2/3 X A plus A X B T plus A square X C T, where A equal to e to the power j 2 pi by 3, that is cos omega t plus j sin omega t, and A square is 240 degree, that is j 4 by 3 cos 4 pi by 3 plus sin 4 pi by 3. And as I have mentioned that it can be a voltage, it can be a current, it can be a flux or any sinusoidally varying quantity. So, thus overall representations in a space vector modulations will be 2/3 of x a by t plus x b by t plus x square by x c. Now, let us consider that 3 phase sinusoidal voltages. So, there you know that we have sin omega t, we have sin omega t minus 120 degree, we have sin omega t plus 120 degree, and thus we require to have this kind of waveform required to be generated by the PWM technique. So, let us consider an instantaneous value over the sine wave for this all the 3 phases. For let us say that t equal to T1 and omega t equal to 3 pi by t, that means at 108 degree. So, somewhere here. So, V A will have the 0.95 Vm, V B will be 0.08 Vm, and V C is the most negative phase here, that will be 743 Vm. So, ultimately, so this is the line. So, summation is 0. We require to generate this voltage. How you can generate that voltage? By inverter. So, we can write like this, that is we know that it can be represented by the voltage, current, anything. So, V equal to 2/3 V A plus A stands for 120 degree phase shift B V T plus A square V C T, and let us consider 3 phases of the sinusoidal voltage, where A equal to T1 and omega t equal to 3 by 5 pi, that is 1008 degree that I have told you. Ultimately, you got these voltages. So, let us see, this is the 3 phases 120 degree apart. This value is a V A, that corresponds to 0.95. This corresponds to V B, because it is negative, that corresponds to, because this is a positive V B. So, this is a negative V B of 0.208. Similarly, you have 0.743, this value as your C. Now, you know that You have studied in, even you have studied mechanics, you have studied in class 9 and 10. So, that is the transpositions of the vector one point to another. You can take it the vector to its line of action any point parallelly, you can shift it, and thus you shift this, the voltage is not a vector, it is a phasor, this is just a representation. So, you shift it here, similarly you shift it here and you draw the phasor, and thus this is the resultant voltage of VABB VC. Please understand that if you sum it up algebraically it should be 0, but this is a vector representation that is not 0. Okay. So, this is the way it will rotate, this is a space vector modulation. So, ultimately that this vector we will calculate, that is all. We will tell this value and theta, and from there every information will be contained, that is a art theta representation. In your question assignments this kind of question will come, and for this reason I am teaching with the emphasis. So, this is consider that this is your B axis, this is your C axis, and this is your A axis, and this is the representations instantaneously, and ultimately you have to split them, because if you take the resultant this will be this. So, it will add up, ultimately it will make this. So, 3 phase quantity and this will vary in this phase plane. The 3 phase quantity varies sinusoidally with the time frequency f, and space vector rotates at a speed of omega, that is equal to 2 pi into f, and having a magnitude of the modulation index of Vm. I am coming to the magnitude of it. Now, questions arises how we synthesize the sinusoidal voltages using the VSI. So, this is the representations of VDC, and ultimately we have drawn the switch, but generally we have considered a resistive load. Otherwise, if it is an inductive load, we have not added the complexity that you require the anti-parallel diode, but most of the cases that will be the case. So, these are the 6 pulse converter, something like that. So, how do you work? So, you will have, I will generate the reference VABB VC, that is coming from the modulation technique, and that will be switching these 6 switches. So, let us see, we want VABB VC to follow that VS reference, VB reference and the VC reference, and for this reason how it will work. We know that this is angle. So, from there we can calculate the magnitude, that is 2/3 VA, VB and VC, multiplying with the A and A square, that is just 120 degree phase shift. So, similarly you have 3 neutral voltages. So, it is VAN once you switch on with respect to this, it is VAN plus VNN. Similarly, you have VBN, this voltage equal to V capital BN and NN, and this is Cn, and ultimately this is the common mode voltage, it is called NN. Thus, you can cancel once you add up. So, this is the representations of this voltage. Next presentation will come like this. So, ultimately this summation will give you 0. So, you are left with this part of it, that is the beauty of this space vector modulation, you do not bother about the common mode voltages that going to cancel immediately. So, that is 2/3 VAN VBN plus VCN multiplied by AN square. So, this term is 0. Now, you know that VAN has to be VDC for into SA, and VAN equal to VDC into SB, and VAN equal to VDC. Ultimately, you got these switches. This is SA can be, that is a leg at representation. It can be 1, then upper switch is on. It can be 0 if lower switch is on, and thus we can write in terms of the switching instead of the voltage. So, you can take this DC bus voltage outside. So, this modulate this magnitude of this voltage will be 2/3 VDC by 2/3 VDC SA SB into 120 degree phase shift and SC equal to 120 degree phase shift. So, this is the representations of the in terms of the switching. So, next, so this is the representations of the space vector modulation. Due to lack of time, I require to stop here right now. Thank you for your attention. I shall take these discussions from your next class from this. Thank you so much.